Greetings and welcome to GILFORD'S lectures. So today we'll be looking at the typical medicine question, and the question reads: the diagram below shows three charges, each of charge 8.85 times 10 to the negative 12 coulomb. The electric field strength at the point Q0 due to the other two charges is, so they want you to get the electric field strength at the point Q0, that is the point where the charge Q0 is found, due to these two charges Q1 and Q2. The distance between the charge Q1 and Q2 is 20 centimeters, while the distance between the charge Q2 and Q0 is 10 centimeters. You are given options A, B, C, and D. Effectively, you need to analyze this question, and your analysis should be related to finding the electric field strength at this point Q0. Let us do that. So now remember that you were asked to find the electric field strength at a particular point where a charge Q0 was located. So it's important for you to know the definition of the electric field strength, that is to know what electric field strength is, and a defining equation for the electric field strength. Actually, every charge creates an electric field, and every electric field has an electric field strength or an electric field intensity. When another charge is placed in it, we are able to determine the strength of that field at a particular point or at different points in the field. So electric field strength is a quantitative expression of the intensity of an electric field at a particular location, or it is the electric force acting per unit small positive charge at a point placed in a medium a distance r from a large charge. So let us consider a large charge as such, where this is the line passing through the center of the charge, and a small charge called the test charge as such, where this is the line passing through the center of the charge. Then the distance between the centers of both charges is given by r, and there's always an electric force F equals 1/4 pi epsilon 0 Q naught on r squared between the two charges. Notice that these two charges are positive charges, so let's assume they are positive charges. Then the electric force acting between the two charges is a force of repulsion, as you can see. So there is a certain quantity called the electric field strength, which is always directed away from a positive charge, and it is given by E. So this electric field strength defines the intensity of the electric field created by this charge at the point where this small test charge has been placed. So the electric field strength at this point is different from the electric field strength at this point, different from the electric field strength at this point, and different from the electric field strength at different points. Effectively, for us to be able to calculate the electric field strength, then we are going to use definition 2, that is this definition, the electric force acting per unit small positive charge. So this is the mathematical expression of the definition, and since the electric force F is given by 1/4 pi epsilon 0 Q naught on r squared, then replacing this expression for F in the expression for E and dividing it by Q0, we notice that this Q0 is going to cancel this, and we are going to be left with 1/4 pi epsilon 0 Q on r squared. And this is the defining equation for the electric field strength. You notice that the electric field strength depends on the charge Q, that is this charge, and also depends on the distance r between this charge and the test charge or any other charge in this medium. So if you reduce the distance r, the electric field strength increases. Hence, the electric field strength at this point is greater than the electric field strength at this point. And as you move closer to this charge, the electric field strength is generally greater than when you move away from this charge. So now, going back to our question, to apply the knowledge we have obtained above to solve it better, we are going to notice that the charge Q1 is at a particular distance from the charge Q0. This distance is given by the sum of the distances between Q1 and Q2 and Q2 and Q0. Effectively, since the distance from the charge Q1 to the charge Q2 was given by 20 centimeters, and the distance from the charge Q2 to the charge Q0 was given by 10 centimeters, then the distance from the charge Q1 to the charge Q0 will be given by 30 centimeters. We are going to call this distance R1 for convenience in our calculations. So R1 is equals to 20 plus 10, which is equal to 30 centimeters. So the total distance from the charge Q1 to the charge Q0 is 30 centimeters. And the electric field strength created by the charge Q1 at the point where the charge Q0 is found will be given by EQ1. Also, remember that the charge Q2 is at the distance R2 equals 10 centimeters from the charge Q0. We're not given the distance as R2, but we're giving it as 10 centimeters. I'm calling it R2 to simplify our calculations, as you are going to see. And the electric field strength that will be created at this point due to this charge will be given by EQ2. Therefore, the net electric field strength created by the charge EQ1 and EQ2 will be equal to the sum of both electric field strength. So the net electric field strength E is equal to the sum of EQ1 and EQ2. So now at this level, we are done with our analysis. Let us move straight into calculations. The very first thing to notice here is that EQ1 is equal to 1 over 4 pi epsilon 0 Q1 on R1 squared, and EQ2 is equal to 1 over 4 pi epsilon 0 Q2 on R2 squared. E, the net electric field strength, is given by the sum of EQ1 and EQ2. So if you take these two quantities and you sum them up, you are going to obtain 1 over 4 pi epsilon 0 Q1 on R1 squared plus 1 over 4 pi epsilon 0 Q2 on R2 squared. Remember that Q1 is equal to Q2, which is equal to a common quantity, so we can let them to be equal to a common quantity Q. But notice that Q1 is equal to Q2, since the magnitude for both all the three charges were the same. Hence, we say that Q1 is equal to Q2. So if we replace Q1 and Q2 by Q and factor out Q, we are going to obtain this quantity. Also notice that since epsilon 0 is equal to 8.85 times 10 to the negative 12, hence the magnitude of Q1 is equal to Q2 and is equal to the magnitude of epsilon 0, which is equal to 8.85 times 10 to the negative 12. So these two quantities will cancel out, and we are going to obtain E to be equal to 1 over 4 pi into 1 over R1 squared plus 1 over R2 squared. Effectively, we need to replace R1 and R2 by their numerical values in the expression for E. So notice that R1 is equal to 20 plus 10, which is equal to 30 centimeters, and 30 centimeters corresponds to 30 times 10 to the negative 2 meters. And also R2 is equal to 10 centimeters, which is equal to 10 times 10 to the negative 2 meters. So now if you replace the values for R1 and R2 in our expression for E, that is R1 which is equal to 30 times 10 to the negative 2 meters, and R2 which is equal to 10 times 10 to the negative 2 meters, in our expression for E, we are going to obtain E to be equal to 8.9 Newton per coulomb, and we can conclude that our solution is D. Please, if you love the video, please like the video, share, and drop at least a comment in the comment section. Those comments go a long way to encourage us. Please share to your WhatsApp contacts. Share even to those who are not writing any concours. Share to friends and family, because someone must get educated after watching this video.